Einstein was remarkably successful in that way, short and to the point. What's amazing is that he managed to invent mainly all of cosmology before anybody had actually ever done any of the observations. Now, to Eddington, that seemed remarkable. And it also seemed a bit suspicious to Eddington. How can you do that anyway? There's some kind of interplay going on here between the physicist and what people think. Right? There's something whereby physics is not just some mechanical thing, it's got some kind of inspiration involved in it. Anyway, that was Eddington's view. Contrariwise, at the present time, we are involved in spending billions, with a B, dollars, on certain kinds of experiments, including this one. Some of you will recognize this. It's the Large Hadron Collider, or a part thereof. And science at the present time has gotten so expensive in terms of experiments that it needs all of the countries of the world to unite to do a good scale experiment. And you can reasonably ask yourself if we have not in fact gotten to the stage where the whole thing is becoming self-defeating. It's too expensive. So for those people that would like to know about the experimental properties of particles, I hope for their sake that the Large Hadron Collider does in fact work. Whether it does or not is a different question. But Eddington would say, why the hell are you spending $1 billion on this? Why don't you give the $1 billion to, say, 100 very bright people, give them $100,000 a year and ask them to figure it all out? It's not something to be laughed at, because in effect that's what Einstein did about cosmology. Of course you can do things by experiment, but it's a crude, nuts and bolts approach to things. Let's go on, and we'll turn now to a situation in astronomy that more or less backs up what I'm trying to say. This is a picture of Olbers, who is a Prussian astronomer who famously asked the question of why the night sky is dark. It's about the simplest question you could ask, isn't it? And any of you sitting here can go out in your backyards tonight and look up and verify it. We're so used to it that we take it for granted, don't we? I did as well, until I started to look at it. And the problem with the thing is that, of course, the night sky is dark. But now think, it's populated by galaxies. Whether they're stars or galaxies makes no difference to the argument. You've got light sources, which are supposed to extend forever and ever through space. There is no boundary. And they are pumping out photons, particles of light. As you carve up the universe into segments, the volume goes up like 4/3 pi r cubed. The intensity of any one source goes down like 1 over r squared. As you take bigger and bigger sections, you're taking more and more stars and galaxies. The conclusion has to be that the sky should be ablaze with light, not black. Obviously there's something wrong, and the problem has become known as Olbers paradox. In the form that I've just described it, it dates from about 1820. It came out in different versions and different articles in 1823 and 1826. You can see straight away that there's something wrong about the way in which people are thinking about this problem. The fact that it's such a blatant contradiction with experience tells you that there's something wrong in the way in which a person is thinking about it. And I remember puzzling about this and thinking, well, God damn it, it's a very simple problem. The answer must be simple. Unfortunately, the answer is not that simple. What's happening, as in regard to modern cosmology, if you've got galaxies like the Milky Way pumping out photons. They've been doing it since they formed, about 13 billion years ago. Presumably, when the Milky Way and the other galaxies formed, space was empty, ergo black. So it started from a state of total blackness. The galaxies and the stars in them begin to fill up space with photons. The photons go into intergalactic space, the background level of radiation starts to rise. If Olbers was right, it would now have risen to a great height so that it's all about as bright everywhere else as it is around here in the face of the sun, right? Because you're basically talking about stars like the sun as the basic sources. There's something wrong. What is wrong? Well, the universe is expanding. All the galaxies are removing themselves from each other in accordance with Hubble's law. There is no center and there's no boundary, but that's okay. You can blow up the whole lot like a balloon. And if you blow up something like that, two things happen. One is that the volume increases, obviously. So one potential answer to the paradox is that the density of photons goes down because the universe is expanding. The other thing which comes along with that is that the energy of any one particular photon is going to go down because of the redshift law, which is given by Planck's law. E equals h is constant times the frequency. So if the energy of any one photon is going down because of the recession and the space to be occupied by all the photons is increasing, you've got a double-barreled effect trying to drag down the intensity. So now we start to get towards a resolution. You've got the galaxies pumping out photons, and these other two effects I just mentioned trying to decrease the level. The question then becomes a much better scientific one. All right, these things are all going on. The problem is obviously time dependent. What is the average intensity now? What is the intensity as balanced between the galaxies all trying to pump out energy and the expansion of the universe and the redshift effect trying to decrease energy? You can do that problem. It's not a difficult problem to describe, but it's rather a difficult one to solve because you have to put in the equations of general relativity to correctly describe the motions and the density of the galaxies. You can do the problem, okay? And again, to cut a long story short, the answer agrees with observation. However, the critical thing here is, like Eddington would have pointed out, you could have solved all this in your brain without having to go to some complicated system of observations. Think about what it is really that you're talking about. The galaxies are emitting the photons. The universe is expanding. The redshift is going to decrease the energy. But wait a second. We know that it started at total blackness. Aha. The photons are coming to us from the other galaxies. We aren't getting the photons from the galaxies so far away that they haven't had time to communicate with us. There are galaxies out there that we have never seen. If the age of the universe is something like 13 billion years, the galaxies farther away, there could be millions and billions of them, but we don't know about that. They haven't sent us their photons yet. That's the solution to the problem. And as Eddington would have pointed out, you could have solved that by sitting down clear-headedly with a sheet of paper in an afternoon. Instead of which we've had arguments going on since about the year 1823 involving massive telescopes to resolve it. The problem is called Olbers paradox, and you'll find it well documented in the literature. The critical point in resolving it is that the universe has a finite age. It hasn't always existed. So roughly speaking, something like the age of the universe times the speed of light shows us how far away we can see. There could be all kinds of stuff beyond that, but we don't know about it. That's the critical resolution. This is actually what the night sky does look like at various wavelengths. On the left-hand side, what I've got here is the radio band, about wavelengths of a meter or 10 meters or so. This diagram has got a lot of information on it, so let's just concentrate on the critical things. This significant